Now you have to be careful with this partial pressure of vapor at the top, 0, and then the interface is 0.1 bar. So basically, if we started with the top itself, so for example, we have this layer of benzene. This is actually the surface top. So if you set this equal to x sub 1, then of course the small layer of a fluid that's actually 30 centimeter. This one is 30 centimeter. So this is our x sub 2, and then the pressure here is P of x sub 1, and then this one is P of x sub 2. So you don't get confused with this, because the partial pressure of the vapor at the top is actually the one it's talking about. So that's Px1 or the Pa1, that's 0, and then of course Px2, the layer at the interface. So basically this is the pressure at which the column ends, so that's 37, and then this is actually air. So that's the pressure at x sub 2. We have convective mass transfer, and we did have convective heat transfer, and the idea of mass transfer is just the same for heat. It's just that we have a concentration boundary layer that is formed from the movement of mixture A and B along the path or the boundary. So this is actually the profile of that, and the dimensionless number that we use here has the same analogy as that of the heat transfer. So that's Schmid number. So it's like the Prandtl number of this mass transfer. So you could just imagine Prandtl number being translated to mass transfer, and then that becomes Schmid number. Now the Schmid number is given by the momentum diffusivity V and divided by the mass diffusivity. So this momentum diffusivity, you can visualize this as if it's the viscosity divided by the the absolute or dynamic viscosity divided by the density. So that gives us the kinematic viscosity of this fluid. And if you want to incorporate that in other correlations, we will be able to get the Sherwood number, which is a function of the Reynolds number and the Schmid number. So before, we used to have this Sherwood number as if it is the Nusselt number. So it's like Prandtl number is kind of congruent to Schmid number in terms of mass transfer, and then this Nusselt number in terms of convection is something like related or kind of congruent to Sherwood number, because we're talking about mass transfer here. That's basically the Reynolds number as the Sherwood number as a function of the Reynolds number and the Schmid number. And as you can see from this expression, that looks like something like the Nusselt number. We have H sub m, and then that's X, and then dA sub B. dA sub B is something like the thermal conductivity in our conduction. So in this, or convection. In this case, it is replaced by the mass diffusivity, and then this H sub m is the convective mass transfer instead of convective heat transfer. And X, of course, is the element that we're concerned of. If it is longitudinal, then we're concerned with the diameter. But if it's kind of vertical, so we're concerned with the length of the pipe, if that's the case. So in addition, as you can read from here, the convective heat transfer can be related through Lewis number, or it can be obtained using the Lewis number. So this Lewis number actually relates the the convective heat transfer to the convective mass transfer. And in this case, if we have the expressions, that's the convective heat transfer coefficient, and this one's the mass, that's actually equivalent to density Cp, or the density times specific heat capacity, divided by the Lewis number raised to 2/3 power. So that's it for our value, and usually the Lewis number is given by the thermal diffusivity ratio and then the mass diffusivity. So you can also rewrite this expression in terms of H over H sub m, and then that is equal to density Cp divided by the ratio of the thermal diffusivity to the mass diffusivity, and then you raise this to 2/3. So that's one expression of the Lewis number in terms of the convective mass transfer coefficient and the convective heat transfer coefficient. Now let's have this problem. If we have air, and then that's 25 degrees Celsius, so that's our T. And then we have 20% relative humidity. It flows through a pipe of 25 mm inner diameter, so this is our D. And then the velocity is 5.2 meters per second. Now the inside surface is constantly wetted with water, and a thin water film is maintained throughout. determine the water evaporated per meter squared surface area. So this is like the idea of having a condensation where there is a film that is formed during the process. So what we need here is to relate this in terms of the Sherwood number, the Reynolds number, and then with that, we'll be able to get the water evaporated per meter squared of surface area based on the fact that we have the equation of the Sherwood number. It's like we're doing the convective heat transfer, but in this case, it's mass. So the first thing that we need to do is to find the Reynolds number, and in this case, that's just the same equation, that's dv rho over mu, and in our equation, they have already solved for this. The Reynolds number is always dv rho over mu, and we have it here. That's actually 15.7 times to the negative 6. That's actually in terms of the kinematic viscosity. So that's it for this value. And then of course, if we use the kinematic viscosity, then we don't have to multiply this with the density anymore. So in this case, we just have to multiply this with the diameter, and the diameter is actually 25. So converted, that's 0.025, and then the velocity, that's 5.2. So we have 8,280, which makes the flow turbulent. So if we have a flow that is actually turbulent, then we need to find a Sherwood number expression wherein it relates the Reynolds number and the Schmid number. Now in the Paris handbook, there is this table 5-17, and as you can see it from here, we have a lot of mass transfer correlations for a single flat plate or disc transferred to or from plate to fluid. And if we go back to our problem, we can see that this is actually a film. So a pipe. So we need to find an expression that has a pipe actually that we can actually use instead of having plates. So this is disc and plate, and then we have here also the continuation of that, and we have a lot. So this is a mass transfer for falling films or weathered wall columns. So that's it for our columns. And then finally we have this mass transfer correlations for flow in pipes and ducts transfer from wall to fluid. So this is what we're actually looking for, and we need to carefully select the equation that we'll be using because there are actually a lot. And to do that, let's take a look at the situation based on this, and then we'll be able to determine the correct correlation that we need to use. In this case, we have a tube, and then that's turbulent. So we need to find a situation that's actually tube and turbulent. So this one is tube, laminar, fully developed parabolic velocity profile. So imagine the profile being fully developed. So that's basically the parabolic that we used to discuss when we had this convection introduction. So we have this fully developed concentration profile, so it doesn't give us enough information if it's turbulent. And then we have this tube, the approximate solution for pipes or ducts. Then we have these tubes, laminar flow again. So we have this laminar, fully developed parabolic velocity profile without any information, and then it's kind of very difficult because it has a lot of given. And then finally, at letter Q, we do have these tubes at turbulent flow. Finally, we'll be able to obtain a correlation that's actually turbulent. So starting from Q and then through the other letters, you can see that we have a lot of turbulent correlations. Now, what do you think is the best correlation that we have to use here? So usually the best correlation that you can use is the first one that's given in your correlation. So I would still think that this one is the best because this is the first one that it gave us. So basically it says here that if the Reynolds number is in between 2,100 and then 35,000, you can actually use this equation. So basically if we have the Schmid number that's actually 0.6 and greater than 3,000, so we can use this as the Sherwood number. But before that, before we can able to find our Sherwood number, because we're given with the Schmid number here, let's find the Schmid number first. So remember, the equation for our Schmid number is V over DAB. So that's just simply taking SC, that's equal to V over DAB, and that's simply the kinematic viscosity. So if you want to use the absolute viscosity, you have something like the viscosity divided by the density, and then that's the AB. So this is how it is obtained in this expression. So we have SC, and then since V is already given, so that's 15.7 times 10 to the negative 6, and then you divide this by 0.26. So actually this Schmid number is not obtained, or wasn't obtained from the table. It was actually obtained from the given itself. So to give you an exact value of this Schmid number, that's around 0.6038. So that's the exact value of the Schmid number. And from this equation, we can see that it falls into this category. So we'll just use this because it falls right into the perfect category of the turbulent flow. And as you can see it from our expression, this is very similar to what this solution used. This is the Sherwood number is equal to 0.023 times the Reynolds number is to 0.83, and the Schmid number is to 1/3. So that's basically obtained from the equation at this page 181 of this 77 reference. So you can read the reference from the, at the bottom portion of this book. So that's basically this expression. Then you just have to plug in those values, and you can actually use the more accurate value, which is actually at 4 decimal places. So if you'll be able to substitute that, and you'll be able to get this value again. So you just have to equate this Sherwood number in terms of Km dt over d, where in this K prime m is convective mass transfer coefficient, so that's H sub m. And then to do this, just have to multiply that with our mass diffusivity constant, so that's the AB. So we have 34.65 times this t, which is actually equal to this 0.26. That's why we have this 34.65 times 0.26. Then we divide that with dt, and dt is actually the diameter, because we're talking about pipes here. So that's 0.025 based on our given. So that's it. And then we'll be able to obtain a value of 0.036 convective mass transfer coefficient in terms of meter per second. And that's actually the convective mass transfer coefficient. We need to use this in order to find the mass flow of the evaporated water. Now let's talk about this 0.023 that's obtained from the table. So we need to take the value of the density at saturation, so that's 0.023, and we'll be talking much in detail about this when we come to humidification. But just for now, it's the density of water at saturation obtained from this temperature 25 degrees Celsius, and then if you subtract this saturation density multiplied with the percent relative humidity, you'll be able to obtain the amount of vapor that's actually being evaporated, and that's typically the water itself in the system. So that's it. If you multiply that, you'll be able to obtain the value of the water evaporated, and then the surface area per meter squared. We need to convert each meter squared area per meter length into 1 meter square to each centimeter length, something like that. So that's 1 divided by pi times 0.025. So that's basically pi times the diameter. So it's like taking this pi d as our length. So that's it for our length of pipe. So we have 12.73 if you want to take the reciprocal of this value. So that's it for our mass flow. So the answer is this one. So why is it that we need to subtract this 0.023 times 0.20 from 0.023? So basically, what we're dealing with is not a water vapor that's actually saturated. So to be able to obtain the true water vapor at this problem, we need to subtract the amount of water that's actually giving, or that's giving off this value of relative humidity. So if you subtract that from our saturation, then we'll be able to obtain the true, something like the true density of water vapor in our system. So that's actually around 0.0184. So that gives us the exact value of our density. So that's it for our example in cases where we need to find the convective mass transfer coefficient. And here's another one, and it says here that we have a thermometer whose bulb is covered by wetted cloth, that's 20 degrees Celsius, and then we need to find the temperature of the air. This is actually the problem as for the dry bulb temperature of the air, because this reading is what we call the wet bulb temperature, and this is exactly the definition of what a wet bulb is. And basically this discussion is intended for humidification, so I'll just be giving some quick insights on how this works, but I'll not be dealing with the technical computations because this is intended for humidification itself. I just want to give you idea on the mass transfer that happens in humidification. So let's start with the energy balance here in convection. So this is the general expression that we use in convection, and it says here that we have the convective heat transfer coefficient, the area, and then of course this TA minus TT, which is the temperature at the surface area and then the temperature at the thermometer reading. So that's basically the sensible heat change that we have. And then we need to find this mass times the enthalpy of evaporation in such case, because water is actually evaporating in this case. So we can also express this in terms of lambda V, assuming that that happens at a certain constant condition of temperature. But for the sake of this expression, let's just use HFG. So the mass is evaporated given by this expression, and instead of using the temperatures, let's just give to this fact that the convective mass transfer coefficient is actually multiplied with this temperature or concentration gradient. So we have this mass transfer coefficient, concentration of the water vapor in air, and then this concentration of water vapor in air at the thermometer surface. So with that, Ca is equal to 0, and this reduces to the final equation of H TA minus TT, and that's HMCT and then HFG. So knowing that temperature is actually 20 degrees Celsius, we assume that this is the saturation temperature. So we need to find the values at saturation. So our fluid here is water and of course air. Now, if we'll be dealing with the ratio of H over Hm to find the Lewis number, that's just saying that we have H of H sub m. From this equation, we know that that's actually C sub T and then HFG over TA minus TT. Okay, and then we don't know the value of our T sub T because that's actually the thermometer. We don't know the value of T sub A because that's actually the temperature of air, and that's the one that we're looking for. But we know that T sub T is 20 degrees Celsius. And to find the CT and then HFG, we obtain that from the given that we have a saturated 20 degrees Celsius temperature. So we'll be using humidification here. I'll just be skipping the solution. It's just that the answer will give you this value. That's CT is equal to 1 over 57.791 kilograms per cubic meter. And in the exams, I will not be giving something like this that will involve, well, I will not be giving this because humidification is a separate topic in the finals. Just to give you a quick idea on how this CT is obtained, we have a saturation humidity obtained from saturation temperature at 20 degrees Celsius, and then we multiply this with the density of air. So that's basically what happens, and then you'll be obtaining this amount of water vapor in air. But that's just for humidification. Anyway, so let's proceed. And this HFG, you can determine this from the thermodynamic properties, although not as accurate as the one from Paris Handbook. So let's just copy this. Okay, so now we're pretty much done with all of these values. So we have this and then we have this, but we don't know this yet. And from this, we can actually relate this expression. This alpha over d is supposedly given to you, so that's 0.790. And then when you evaluate further, the density is obtained from the qualities of air, that's at T equals 20 degrees Celsius, and you'll be able to obtain this value. So starting from this, we have h over h sub m. So we have this formula right here, and we know that you can use this density, so that's 1.205. This is that density, and then of course the specific heat capacity is also obtained for air, so that's 1005, and then we multiply that with the ratio of alpha over d, that's 0.790. So actually this can be simplified into 0.790. So we raise that to to 2/3, and then we'll be able to obtain this value. Now plugging this value with all of these, you can actually solve for the TA. So you have h over h sub m that is equated to this expression. So we have around 1034.65. Okay, and then if you equate this value, you'll be able to obtain this expression, and then that's 20 plus 1 over 1034. We divide this with CT, or we multiply this with CT, and then this is the enthalpy of evaporation. So with this, we have 61 degrees Celsius. Now the easiest way to check this is to use psychrometric chart based on this expression, but we'll be saving that for our future discussion. It's just that I want to show you how this is related to the free convection or the heat transfer by convection. And of course, if I'll be giving you something like this, I will make sure that I will give you the concentration of water over air, and of course the relationship of Schmid number and Prandtl number at this case, because it's kind of difficult to determine if you don't have knowledge in psychrometry. Okay, so that's it for our steady state mass transfer. Now let's move on to transient and interphase mass transfer. Now there are cases wherein we have dilute systems, and of course we have the concentrated system. Where is that? This one. Now if we were talking about these dilute systems, we know that when we have let's say a mixture, and then the solute is kind of like very small compared to the whole mixture or the solvent. Basically what we have is a dilute system, and this dilute system, you can read all about this relationship in terms of the mass transfer rate, the gas phase mass transfer coefficient, the liquid phase mass transfer coefficient. But I'm much more concerned with, and of course this we have this molar liquid mass, molar gas liquid velocity. These are just expressions used instead of expressing it in terms of fixed laws. So you just have to rearrange these expressions, then you'll be able to obtain this expression, and finally you'll be able to get this expression, and that's actually one of the most important here. But I'm much more concerned with this graph here. This is a graph that we use usually in gas absorption, and luckily we have this in interphase mass transfer. So what we have is the operating line, and then this is the equilibrium line, the curve 1. So whenever you have something like a tangent, or not a tangent, but a line that connects this equilibrium line to a point somewhere at point 1 and point 2, the slope will always be something like this. The y sub I minus the equilibrium condition minus x sub I minus x at any value of x. And then if you project this to the operating line, you will be able to get that tangent line to this portion. So basically it's tangent here. So what you will be getting is a slope that's called the negative KL over kg. So usually this is slope, the one line that connects this any point here perpendicular to the operating line from the equilibrium line, is what we are able to obtain from the Henry's law. So we know that Henry's law is an expression wherein we can find the partial pressure of a certain compound with respect to the Henry's constant. So if we try to relate this Henry's constant in terms of the operating line connected by this slope of KL and kg, then that's actually the Henry's constant. That's why this is very important in equilibrium curves and gas absorption. So this is the most important thing that you need to remember here in interphase mass transfer and in dilute systems. Of course, it's kind of different when we talk about concentrated systems, but the idea is just something like this. The mass transfer rate is equal to this kg times y minus y sub I over y sub ybm, wherein ybm is this very long expression that's just 1 minus y, 1 minus 1 minus yi, and then you have this expression as simplified. And later on, you'll be able to understand what this yi mean, what does y mean, and then this something like this x raised to degrees or whatever are those things. But one thing is for sure, we'll be evaluating those conditions when we talk about equilibrium conditions, the minimum conditions, and of course those conditions that are existing in a way that they exist in the operating line and of course in the equilibrium line. And from this graph, you can already see that the operating line is where xy lies or lie. And then for the equilibrium line, as you can see from here, these are the values of x, x raised to something like degree or x degree, or we call this the x asterisk, and then this one is the y asterisk. So those are the conditions where we'll be using some notations. And then we have this HTU. Now this HTU is actually the height equivalent to one transfer unit. So this is usually used when we want to give the dimension of, let's say, a column based on this HTU. And if you're given with this, you can relate that in terms of kg and then kl, and then you'll be able to get this HTU. And this is related to the number of transfer unit. So if you have this HTU, and then you have this value of HOG and then NOG, then actually you can determine the other unknowns from this expression. But of course, we'll be paying attention with mass transfer first before we are able to solve this number of transfer unit. Okay. Now the example for this, I want to save that in another video so that we have a more thorough discussion regarding transient and interphase mass transfer. Okay.